What if everything we know, every star, every galaxy, even the boundaries of our universe, is just a speck in something far grander? Picture standing at the edge of an endless ocean, staring into the horizon, wondering what lies beyond what your eyes can see. That's exactly where we find ourselves when we try to grasp what might exist outside the known cosmos. Our universe stretches 93 billion light-years across, filled with uncountable galaxies, each hosting billions of stars. And yet, scientists suspect this might just be the beginning. The truth is, the deeper we look, the more we realize how little we truly understand. For centuries, humans have gazed at the night sky, asking one timeless question: what's out there? But today, we're not just wondering about distant planets or alien life, we're peering beyond the very fabric of our reality, into realms where physics as we know it might break down. Some theories suggest parallel universes bubbling up like foam in an infinite cosmic sea. Others propose we're living inside a black hole, or that our universe is just one page in an endless library of realities. The possibilities are as thrilling as they are terrifying, and they challenge everything we thought we knew about existence itself. That's why we're diving into 25 of the most mind-bending theories about what lies beyond our universe. From the holographic principle to the multiverse, from cyclical cosmos to higher dimensional realms, each idea is a window into the profound mysteries that haunt scientists and dreamers alike. Some of these theories might sound like science fiction, but they're rooted in cutting-edge mathematics, quantum physics, and the boldest cosmological observations. So if you've ever felt that tug of curiosity, that nagging sense that there's more to reality than meets the eye, you're in the right place. This journey isn't just about facts, it's about stepping to the edge of human understanding and daring to look beyond. Strap in, we're about to explore the impossible. The first and perhaps most famous theory about what lies beyond our universe is the staggering idea of the multiverse. Imagine a vast cosmic tapestry where instead of one universe, there are infinite others, each with its own unique set of physical laws, constants, and even dimensions. Some might contain gravity so weak that matter never clumps into planets, while others could be ruled by forces we've never seen. This isn't science fiction, it's a legitimate scientific hypothesis, backed by some of the most brilliant minds in physics. At its core, the multiverse theory emerges from two key pillars of modern science: quantum mechanics and inflationary cosmology. Quantum mechanics tells us that particles exist in a haze of probabilities until they're observed, suggesting countless parallel realities where every possible outcome plays out. Meanwhile, inflationary cosmology, the idea that our universe expanded exponentially in the first fraction of a second after the Big Bang, hints that this rapid stretching of spacetime could have created bubble universes, isolated from each other like soap suds in an endless froth. One of the most vocal supporters of this idea was the legendary Stephen Hawking, who saw the multiverse not as fantasy, but as a natural consequence of the laws governing reality. In his final paper, he even proposed a way to test the theory by hunting for cosmic imprints left behind by collisions between our universe and neighboring ones. And he wasn't alone. Nobel laureate Brian Greene likens the multiverse to an infinite cosmic quilt, stitched together by the very fabric of quantum uncertainty. But here's where things get truly mind-bending. If the multiverse exists, it could explain one of the biggest mysteries in science: why our universe seems so perfectly fine-tuned for life. A single tweak to gravity, electromagnetism, or the strength of nuclear forces would make stars, planets, and us impossible. In an infinite sea of universes, however, it's statistically inevitable that at least one would have the right conditions by pure chance. We might not be special, just lucky. Of course, skeptics argue that the multiverse is untestable, more philosophy than physics, yet cutting-edge experiments like searching for unusual patterns in the cosmic microwave background could one day offer clues. Either way, the idea forces us to confront an astonishing possibility that our universe, with all its billions of galaxies, might just be one tiny corner of something unimaginably vast. And if that's true, the real question isn't just what lies beyond our universe, but how many versions of us might be out there, living in realities beyond our wildest dreams. But the multiverse isn't just one idea, it's a whole family of theories, each painting a radically different picture of what might exist beyond our cosmic horizon. Let's start with bubble universes, one of the most well-supported versions. Picture an endless, frothing sea of spacetime, where new universes constantly pop into existence like bubbles in a boiling pot. According to inflationary theory, our universe might be just one of these bubbles, forever drifting apart from others due to the relentless expansion of space. Some of these bubbles could harbor physics entirely alien to ours, perhaps with no stars, no atoms, or even no light. Others might be nearly identical, with doppelganger versions of Earth where history unfolded just slightly differently. Then there's the many worlds interpretation of quantum mechanics, a theory so bizarre it feels ripped from a Chinese letter novel. Every time a quantum particle faces a choice like whether to spin left or right, the universe doesn't pick one outcome. Instead, it splits into two, creating parallel timelines where every possibility plays out. Missed a bus this morning, in another world you caught it. Lost a coin toss, somewhere else you won. This isn't just philosophical musing equations in quantum physics actually support it. The catch, these alternate worlds remain forever out of reach, like ghostly reflections trapped in a cosmic hall of mirrors. But perhaps the most radical vision comes from Brane-World theory, born from string theory's tangled mathematics. Imagine our universe as a three-dimensional membrane, floating in a higher dimensional space, like a single slice of bread in an infinite loaf. Other branes could hover mere millimeters away in these unseen dimensions, each hosting its own universe, yet we'd never know, because gravity is the only force that might leak between them. Some scientists speculate these hidden branes could even explain dark energy, or that catastrophic collisions between them might trigger new Big Bangs. What ties these theories together is their audacity. They force us to confront the unnerving possibility that everything we see, the stars, the galaxies, the very fabric of reality, might be inconceivably small compared to what's really out there. Whether it's bubbles, branches, or floating membranes, each model challenges our place in the cosmos. And while we can't yet prove which, if any, are true, their mere existence reshapes humanity's oldest question: are we alone, or is the universe teeming with versions of itself, each stranger than the last? What if everything you see, touch, and experience, every mountain, ocean, and galaxy, is nothing more than an illusion, a cosmic mirage painted onto the fabric of reality like a hologram on a credit card? This isn't the plot of a sci-fi movie, it's the startling premise of the holographic universe theory, one of the most radical ideas in modern physics. At its core, this theory suggests our three-dimensional world might actually be a projection from a two-dimensional surface lurking at the edge of everything we know. The roots of this mind-bending concept trace back to an unexpected place: black holes. In the 1970s, physicist Jacob Bekenstein discovered something bizarre. The amount of information a black hole can hold isn't proportional to its volume, but to its surface area. Later, Leonard Susskind and Gerard T. Hooft took this further, proposing that all the information inside a black hole could be encoded on its boundary, like a cosmic DVD. Fast forward to the 1990s, and string theorists like Juan Maldacena realized this principle might apply to the entire universe. Imagine the cosmos as a giant black hole, with every star, every atom, every thought you've ever had simply being data etched onto a distant, two-dimensional shell. But how could a flat surface create the rich, three-dimensional world we inhabit? Think of it like a movie screen. When you watch a film, flat pixels trick your brain into seeing depth, movement, even emotion. The holographic universe suggests reality works the same way, except the screen is the edge of existence itself, and the pixels are unimaginably tiny units of information called Planck-length bits. Even stranger, this might explain why quantum particles can become entangled across vast distances, because at the fundamental level, they're not separate at all, just reflections of the same underlying code. So how do we test something this extraordinary? Scientists have proposed wild experiments, like searching for pixelation in the fabric of spacetime using ultra-sensitive gravitational wave detectors. Others analyze the cosmic microwave background for subtle glitches, anomalies that might reveal the universe's true, lower-resolution nature. If proven, the implications would rewrite physics. Time, space, even consciousness could emerge from this hidden, flat reality like a shadow cast by firelight. The holographic universe doesn't just challenge what we know, it asks whether reality is even the right word. Are we solid beings, or fleeting patterns on the surface of something far deeper? Either way, one thing's certain: the universe is stranger than we ever imagined. The idea of a universe with no true beginning or end is both haunting and beautiful. What if the Big Bang wasn't a one-time event, but just the latest chapter in an infinite cosmic saga? This is the heart of the Cyclic Model, a theory that rewrites the story of our universe as an endless loop of destruction and rebirth. Imagine a cosmic phoenix rising from its own ashes over and over, each cycle birthing new galaxies, new stars, and perhaps even new life. At its core, the cyclic model hinges on dark energy, that mysterious force accelerating the expansion of our universe. Most theories treat dark energy as a constant, but here's the twist: what if it isn't? Some versions of the cyclic model suggest dark energy could weaken over time, eventually allowing gravity to reverse the expansion. Galaxies would slow, then hurtle toward one another in a catastrophic, big crunch. Space and time would collapse into an unfathomably dense point, only to rebound in a new Big Bang, resetting the cosmic clock. The cycle could repeat indefinitely, with each universe inheriting faint echoes of the one before. This idea isn't new. Ancient Hindu cosmology spoke of universes breathing in and out over trillions of years, but modern physics gives it teeth. Pioneered by theorists like Paul Steinhardt and Neil Turok, the cyclic model avoids the need for a singularity, a point of infinite density at the Big Bang that breaks Einstein's equations. Instead, it proposes a smoother transition, with collisions between higher dimensional branes, from string theory triggering each rebirth. Think of it like two sheets of paper slapping together in a fourth spatial dimension, unleashing enough energy to forge a fresh cosmos. Yet the cyclic model faces fierce debate. Critics point out that entropy, the universe's tendency toward disorder, should accumulate across cycles, making each new universe more chaotic than the last. If true, why does our cosmos appear so finely structured? Supporters counter that certain quantum effects could reset entropy at each bounce, though this remains speculative. Others argue that dark energy's behavior shows no signs of weakening. Our universe seems destined for eternal expansion, not collapse. Still, the cyclic model offers something profound: a universe without a true death. Stars may fade, black holes may evaporate, but existence itself would continue, eternally reinventing itself. It's a vision where endings are just beginnings in disguise, and where the story of everything might be far grander than we ever dreamed. What if everything around you, every person, every star, every law of physics is nothing more than lines of code in an unfathomably advanced simulation? This is the jarring premise of the simulation hypothesis, a theory that straddles the line between cutting-edge science and existential philosophy. At its heart lies a simple but unsettling question: if civilizations eventually gain the power to create hyper-realistic virtual worlds indistinguishable from reality, how can we be certain we're not inside one? The argument gained traction in 2003 when philosopher Nick Bostrom laid out his now famous trilemma: He proposed that at least one of three statements must be true. Either nearly all civilizations go extinct before reaching technological maturity, advanced civilizations lose interest in creating simulations, or we're almost certainly living in one. There's no fourth option, meaning if even a tiny fraction of civilizations survive and choose to run ancestor simulations, the number of artificial minds would vastly outnumber biological ones. Statistically, the odds tilt heavily toward us being artificial constructs in someone else's cosmic computer, but this isn't just abstract theorizing. Scientists have hunted for tangible glitches that might betray the universe's digital nature. Some suggest examining the fabric of spacetime itself. Just as pixels reveal an image's resolution, spacetime might have a fundamental granularity at the Planck scale, where reality becomes blocky if you zoom in far enough. Others propose searching for computational shortcuts, places where the simulation cheats to save processing power, like slight inconsistencies in quantum behavior or unexpected limits in high-energy physics. Even the infamous double-slit experiment, where particles behave differently when observed, has been reinterpreted by some as an optimization trick, rendering details only when necessary to conserve resources. Tech mogul Elon Musk famously stated the odds we're in base reality are 1 in billions, while physicist Sila's Bean simulated a miniature universe to study how its fake inhabitants might detect their own artificiality. His unsettling conclusion: simulated beings could find evidence by spotting repeating patterns in cosmic rays, a potential signature of a finite cosmic processor. Yet critics counter that the hypothesis is unfalsifiable by nature. Any glitch we find could just be part of reality's true mechanics. Others argue that simulating every particle in a universe would require more energy than the universe itself contains. But proponents fire back. An advanced civilization might simulate only what's observed, like a video game rendering graphics in a player's vicinity. Whether metaphor or reality, the simulation hypothesis forces a profound reckoning. If true, it would mean the stars are someone else's screensavers, the laws of physics are user settings, and every human thought is just an algorithm running on hardware beyond comprehension. It's a theory that doesn't just ask what lies beyond our universe, it asks whether the universe is real at all. One of the most compelling arguments for the holographic universe comes from an unexpected place: the very limits of reality itself. At the tiniest scales imaginable, physicists suspect spacetime might not be smooth and continuous, but grainy, like a digital photograph enlarged until pixels appear. This Planck scale is the smallest meaningful unit of space, about 1/1,000,000th of a trillionth, the size of a hydrogen atom, where the laws of physics as we know them break down. If the holographic principle holds true, this pixelation wouldn't just be a quirk of quantum mechanics, it would be the underlying resolution of the universe's projection, like the dots on a newspaper image revealing the print's true nature. Some researchers have attempted to detect this cosmic pixelation using gamma-ray bursts, the most energetic explosions in the universe. As these high-energy photons travel billions of light-years to reach us, the theory suggests their wavelengths might subtly scatter if spacetime has a granular structure, like light flickering through a frosted window. Initial studies with telescopes like the Fermi Gamma-Ray Space Telescope found no such blurring, but newer experiments propose even more sensitive methods, like analyzing quantum entanglement over vast distances. If particles remain linked across cosmic scales without any degradation, it could imply spacetime is smoother than the holographic model predicts, or that we're not looking at the right resolution yet. But the most heated debate revolves around consciousness itself. Could something as intricate as human experience truly emerge from a two-dimensional data sheet? Critics argue that subjective awareness, the way pain feels sharp or music stirs emotion, can't be reduced to mere information processing. Philosopher David Chalmers famously framed this as the hard problem of consciousness. suggesting that even if we map every neuron in the brain, we might never explain why it feels like anything to be alive. If consciousness requires genuine physicality, not just coded patterns, the holographic universe might struggle to account for the depth of lived experience. Supporters counter with a radical proposition: what if consciousness isn't produced by the brain, but received by it like a radio tuning into signals from a deeper, immaterial reality? In this view, the brain doesn't generate thoughts but decodes them from the universe's fundamental information field. Mystical traditions have hinted at this for millennia, but even sober scientists like quantum physicist Carlo Rovelli suggest reality might be a network of relationships, not substances. If true, the holographic principle wouldn't diminish consciousness, it would elevate information as the true fabric of existence. Yet the debate circles back to a deeper question: can any theory that reduces reality to data ever capture its texture, the warmth of sunlight, the ache of nostalgia, the sheer there-ness of the world? The holographic universe dazzles with its mathematical elegance, but some truths might resist being digitized. Until experiments deliver undeniable proof, this theory remains a breathtaking possibility, one that doesn't just reshape our understanding of space, but of what it means to be at all. Imagine living in a world where up, down, left, right, forward, and backward aren't the only directions that exist, where hidden dimensions curl around us like invisible folds in the fabric of reality. This isn't science fiction, it's the startling premise of the Brane-Worlds scenario, a theory that rewrites our cosmic address. According to string theory, the universe we call home might be a three-dimensional brane, short for membrane, floating in a higher dimensional space, like a single sheet of paper drifting in a vast, unseen library. And if that's true, everything we perceive, from the glow of distant galaxies to the beat of your heart, could be bound to this brane, trapped within its invisible walls like shadows on a cave wall. String theory, the framework behind this radical idea, suggests that the fundamental particles of the universe aren't dots but tiny, vibrating strings. For the math to work, these strings need 10 or 11 dimensions to dance through far more than the 4-3 space, one time we experience daily. So where are these extra dimensions? The Brane-World theory proposes they're compactified, curled up so tightly we can't perceive them, or stretch beyond our brain's reach. Picture an ant walking along a telephone wire. From a distance the wire seems one-dimensional, but up close, the ant knows it can circle the wire's surface, exploring a hidden dimension we'd miss from afar. But here's where things get explosive. Some models suggest our Big Bang wasn't a singular event, it was a cosmic collision, a moment when our brains smashed into another in that higher dimensional void. Like two sheets of paper slapped together, the energy of that impact could have ignited the fireball that became our universe. Even wilder, this might not be a one-time event. Cyclic brain collisions could spawn endless universes, each with its own laws of physics, like echoes in an infinite dimensional hall. The implications are staggering. If brains exist, gravity, the weakest of nature's forces, might be weak because it's leaking into these extra dimensions, diluting its strength like water seeping through a sieve. This could explain why gravity doesn't play by the same rules as electromagnetism or nuclear forces. It's operating on a cosmic scale we can't see. Some theories even suggest black holes might be bridges to other brains, their monstrous gravity warping spacetime so severely that it punctures through to another reality. So how do we test something this abstract? Scientists hunt for tiny deviations in gravity's pull at microscopic scales, where extra dimensions might subtly alter its strength. Others scour particle accelerators for hints of gravitons, gravity's theoretical particles, disappearing into higher dimensions, and if colliding brains really did birth our universe, they might have left faint ripples in the cosmic microwave background, ancient scars from a collision beyond time. The Brane-Worlds scenario doesn't just redefine the universe, it threatens to shatter our sense of place within it. If true, we're not just cosmic accidents on a lonely rock, we're inhabitants of a membrane adrift in a multidimensional ocean, surrounded by realms we may never see but whose existence could shape everything we know. It's a humbling thought. What we call everything might just be a single page in a book with infinite volumes, each with its own laws, its own stories, its own version of reality. If black holes are the universe's ultimate one-way streets, cosmic traps where matter and light vanish forever, then white holes might be their mysterious opposites, celestial fire exits, spewing out everything a black hole swallows. Imagine a cosmic fountain where instead of water, galaxies, stars, and particles gush forth uncontrollably, defying gravity's pull. This is the white hole hypothesis, a theory so bizarre it feels like physics turned inside out. White holes emerge from the same equations that predict black holes. Einstein's theory of general relativity, where a black hole's gravity is so strong nothing escapes its event horizon. A white hole's event horizon repels everything. Nothing can enter, it can only explode outward in a relentless torrent of energy and matter. Some theorists propose these objects could be the other end of a black hole's tunnel, connected by an Einstein-Rosen bridge, the scientific term for what we often call a wormhole. In this scenario, a black hole in one universe might funnel matter through a wormhole, only for it to erupt from a white hole in another. Yet there's a glaring problem with this elegant idea: we've never seen a white hole. If they exist, why are they so elusive? One possibility is that they're inherently unstable. Unlike black holes, which form when massive stars collapse, white holes would require some mechanism to reverse entropy, the universe's tendency toward disorder. They'd essentially be rewinding time, an event so improbable that most would vanish almost instantly, collapsing into black holes the moment they form. Others speculate white holes might only appear in the earliest moments of a universe's life, acting as cosmic pressure valves during the Big Bang itself, releasing the energy that seeded galaxies. But the most radical interpretation comes from loop quantum gravity, a theory attempting to unify general relativity with quantum mechanics. Here, a black hole's collapse doesn't end in a singularity, a point of infinite density, but rebounds like a compressed spring into a white hole. This quantum bounce could transform dying black holes into white holes over trillions of years, meaning the oldest black holes in our universe might one day reverse their nature, spitting back out everything they've consumed. The implications are staggering. If white holes exist, they'd challenge our understanding of time's arrow, entropy, and even causality. They might also solve one of physics' biggest mysteries, the fate of information swallowed by black holes. Quantum mechanics insists information can't be destroyed, yet black holes seem to erase it. White holes could be the universe's failsafe, preserving that data by ejecting it elsewhere, perhaps into an entirely new cosmos. So why haven't we detected one? Some astronomers scan for unexplained gamma-ray bursts or sudden flares of energy with no visible source, potential white hole signatures. Others argue they might masquerade as other phenomena, like quasars or even dark matter. Until we spot one, white holes remain a tantalizing what if, a reminder that the universe's rulebook might have pages we've yet to read. Whether cosmic mirages or hidden gateways, they force us to question: if black holes are the end, could white holes be a beginning? What if the Big Bang wasn't an explosion, but a cosmic car crash? This is the spine of the Ecbiriotic Universe theory, a radical alternative to inflation that rewrites our universe's origin story. Instead of a singular burst from nothingness, this model imagines two parallel worlds, three-dimensional brains, floating in a higher dimensional space, slamming together like cymbals in the dark. The energy of that collision wouldn't just create heat and light, it would forge an entire cosmos, seeding galaxies and stars in the shockwaves of impact. The Ecbiriotic scenario, rooted in string theory, emerged in the early 2000s as a challenger to inflation, the dominant idea that our universe expanded exponentially in its first fraction of a second. While inflation solves many cosmic puzzles, it struggles to explain why the universe appears so uniform on large scales. The ekpyrotic model offers a sleeker solution. Those colliding branes were stretched and smoothed over eons before their crash, like dough kneaded flat before baking. This slow, steady flattening would naturally erase irregularities, leaving behind the eerily even cosmos we observe today, but the theory's real brilliance lies in its predictions. Unlike inflation's chaotic quantum fluctuations, ekpyrosis would imprint subtle, distinctive patterns on the cosmic microwave background, the afterglow of the Big Bang. These patterns would resemble elongated, cold spots stretching across the sky, fingerprints of a universe born not from chaos, but from a controlled high-energy embrace. When scientists analyzed data from missions like Planck and WMAP, however, the results were ambiguous. Some features aligned with ekpyrotic predictions, but others stubbornly matched inflation's playbook. The verdict, the cosmic jury's still out. Critics highlight another hurdle, the singularity problem. If branes collided, wouldn't their meeting point be infinitely dense, a breakdown of physics akin to traditional Big Bang models? Proponents counter that string theory's extra dimensions might soften the blow, with branes interacting smoothly rather than crumpling into a single point. It's a cosmic fender bender where the crash itself is what breathes life into existence. The ekpyrotic universe forces us to rethink not just our beginnings, but our place in the multiverse. If colliding branes birthed us, might other universes be forever ricocheting in unseen dimensions, each crash igniting a new reality? Could our cosmos one day rebound, destined to collide again in an endless cycle? Unlike the inflationary tale of isolated creation, this is a story of connection, a reminder that even the vast emptiness of space might hide bridges to worlds beyond our own. Whether truth or tantalizing speculation, the ekpyrotic model proves one thing: the universe's origin story is far from settled, and as we scour the cosmos for clues, we might find that creation's most dramatic moments weren't solitary, but shared across dimensions we've yet to imagine. Imagine waking up one day with all your memories intact: your childhood home, your first kiss, the smell of rain on pavement, only to realize none of it ever existed. You're not a person at all, but a fleeting spark of consciousness, randomly assembled by quantum fluctuations in an endless void. This nightmare scenario isn't from a horror movie, it's the Boltzmann brane paradox, one of the most disturbing thought experiments in physics. Named after 19th-century physicist Ludwig Boltzmann, the idea forces us to confront a chilling question: if the universe tends toward chaos over time, why does order exist at all? Boltzmann's original work sought to explain why we perceive time moving forward, why eggs smash but never unscramble, why we remember the past but not the future. His answer hinged on probability. In an infinite, chaotic universe, statistically improbable pockets of order must occasionally arise, like waves briefly forming patterns on a stormy sea. But here's the twist: in an eternal cosmos, it's far more likely for a single, self-aware mind to spontaneously form from random particle collisions than for an entire, orderly universe like ours to emerge. Your memories, your senses, even the screen you're staring at, they'd just be an illusion, a flicker of coherence in an otherwise meaningless void. The paradox gains teeth when paired with modern cosmology. If dark energy keeps accelerating the universe's expansion, eventually all matter will spread so thin that space becomes an icy wasteland, a state called heat death. Yet quantum mechanics tells us even empty space crackles with virtual particles popping in and out of existence. Given enough time, say 10 to the power of 50 years, those particles could randomly arrange into a functioning brain, complete with fabricated memories of a life that never happened. And since heat death lasts eternally, Boltzmann branes would vastly outnumber real, biologically evolved minds. By the numbers, you're probably one. Physicists recoil from this conclusion, not because it's frightening, but because it undermines science itself. If most observations come from hallucinating Boltzmann brains, how can we trust any data about the universe? Some theorists fight back by proposing cognitive instability, the idea that a Boltzmann brain's perceptions would be so garbled it couldn't form coherent thoughts, let alone ponder cosmology. Others argue the paradox hints at flaws in our models, like inflation or quantum gravity, that might prevent eternal heat death altogether, yet the most profound implication isn't about brains, it's about time's arrow. Boltzmann's work suggests our experience of cause and effect might be a rare accident in a cosmos without inherent direction. The paradox forces us to ask, is the universe we see real, or just the statistical outlier in an endless sea of chaos? Either answer is humbling. Either we're inconceivably lucky to exist in a cosmos with structure, or we're ghosts in the machine, destined to dissolve back into the noise from which we came. The ground beneath your feet feels solid, dependable, but what if it's all an illusion? What if the very laws of physics holding our universe together are just a house of cards, one quantum flutter away from collapse? This isn't paranoia, it's the spine-chilling premise of the false vacuum theory, a hypothesis suggesting our universe might be sitting in a precarious state of balance, like a marble resting at the top of a hill. One nudge and everything we know, every atom, every galaxy, even time itself could vanish in an instant, rewritten by a fundamental shift in reality's rules. At the heart of this theory lies a peculiar property of quantum fields, the invisible forces that govern particles and energy. Think of these fields as a vast, invisible landscape, with valleys representing stable states and hills marking unstable ones. Right now, the Higgs field, the same field that gives particles mass, appears to be sitting in a false vacuum, a valley that seems stable but actually sits higher than the lowest possible energy state. It's like a ball trapped in a shallow depression on a mountainside. Given enough time, quantum mechanics says it could tunnel through the hill, rolling into a deeper valley where the rules of physics might be unrecognizable. This process, called quantum tunneling, defies classical intuition. Particles don't need to climb over barriers, they can simply appear on the other side, vanishing from one state and materializing in another. If this happened to the Higgs field on a cosmic scale, the consequences would be apocalyptic. A bubble of true vacuum could spontaneously form anywhere in space, expanding at the speed of light, rewriting the laws of physics as it goes. Inside this bubble, atoms might dissolve, forces could cease to exist, and the very structure of reality would unravel. The worst part, we'd have no warning. One moment the universe as we know it, the next, an alien physics we can't even fathom. Some physicists calculate the odds of this happening as vanishingly small, less than 1 in a trillion over billions of years. But unlikely doesn't mean impossible. The universe has existed for 13.8 billion years already, and if it's truly metastable, the clock is ticking. Others argue that cosmic inflation might have locked us into a stable state, making decay impossible, yet experiments at particle colliders like the Large Hadron Collider continue to probe the Higgs field's properties, searching for clues about its true nature. A slight deviation in its measured energy could tip the scales toward stability or doom. The false vacuum theory forces us to confront an uncomfortable truth: the universe might not be permanent, just temporary. It's a cosmic sword of Damocles, dangling over existence itself. And while the numbers might reassure us, they can't erase the haunting question: what if we're already living on borrowed time, in a reality that's just a placeholder for something we can't even imagine? Let's return to the holographic principle, but this time, through the lens of one of physics' most vexing puzzles, the black hole information paradox. At first glance, black holes seem like cosmic vacuum cleaners, sucking in stars, gas, and light with no escape. But here's the catch: quantum mechanics insists information can never be truly destroyed. So what happens to all the data describing the particles that fall into a black hole? Does it vanish forever, violating quantum law, or is it somehow preserved? The answer might lie in holography, and it's reshaping how we think about reality itself. Picture a black hole's event horizon, the point of no return, not as a two-dimensional surface, but as a cosmic hard drive. In the 1970s, physicist Jacob Bekenstein calculated that the maximum amount of information a black hole can hold isn't determined by its volume, but by the area of its horizon. This was the first clue that the universe might encode data in unexpected ways. Later, Leonard Susskind and Gerard T. Hooft took this further, arguing that everything inside a black hole, every atom, every photon, could be fully described by information painted onto its boundary, like a hologram. The three-dimensional chaos within, just a projection of that two-dimensional data, but the real breakthrough came with string theorist Juan Maldacena work in the late 1990s. He devised a mathematical model where a hypothetical universe with gravity like ours could be perfectly mirrored by a lower-dimensional universe without gravity, operating purely through quantum fields. The two descriptions were interchangeable, like a holographic sticker that looks flat until you tilt it and see depth emerge. If this duality holds, it implies our 3D reality might be a shadow cast by quantum processes unfolding on a distant, 2D surface, perhaps even the edge of the observable universe. So how does this solve the black hole paradox? Imagine a book tossed into a fire. In a classical world, it burns to ash and the information is lost. But in a holographic universe, the book's words aren't in the pages, they're etched onto the surface of the fire itself, preserved in the flickering patterns of the flames. Similarly, when matter falls into a black hole, its information isn't destroyed, it's scrambled and stored on the horizon, like a cosmic encryption. Over time, Hawking radiation, the slow leakage of energy from black holes, could carry that information back out, reassembling it in subtle ways we don't yet understand. Critics argue this raises new questions. If reality is a hologram, why do we perceive depth, texture, and solidity? Why does the universe feel so tangible? Supporters counter that even a credit card hologram creates the illusion of 3D. Our brains might be decoding a flat data stream into the rich world we experience. Others point to the ADS/CFT correspondence, a concrete mathematical framework showing how higher dimensional gravity can emerge from lower dimensional quantum systems. It's not just philosophy, it's equations that work. The holographic principle doesn't just rescue information from black holes, it suggests that the universe is fundamentally about information. Space-time, even matter might be secondary, emergent properties of a deeper, more abstract code, and if that's true, it means the cosmos isn't just described by math, it is math, unfolding on a canvas we're only beginning to glimpse. Whether this is the final word on reality or just another step toward deeper mysteries, one thing's certain, the universe is far stranger and far more elegant than we ever dreamed. What if the Big Bang wasn't the beginning, just the middle of an endless cosmic heartbeat? This is the daring promise of the Big Bounce theory, where the universe doesn't end in heat death or a big crunch, but rebounds into a new cycle of existence like a phoenix rising from its own ashes. At its core, this idea challenges the notion of a singular, definitive origin, proposing instead a universe caught in an eternal dance of collapse and renewal. Loop quantum gravity, the framework behind the Big Bounce, rewrites Einstein's equations to avoid the dreaded singularity, the point of infinite density where physics breaks down. Instead of a dead-end collapse, the theory suggests that as matter compresses beyond a critical threshold, quantum forces create a repulsive effect, like a spring coiled too tightly suddenly releasing. Space doesn't vanish into oblivion, it bounces, transforming the final moments of one universe into the first sparks of the next. Picture a cosmic trampoline, the deeper the collapse, the more powerful the rebound, with all the energy and structure of the old universe recycled into a fresh expansion. This stands in stark contrast to the Cyclic Model, where universes collide in higher dimensions to trigger rebirth. While both theories reject the idea of a one-time Big Bang, the mechanisms differ dramatically. The cyclic model relies on branes slamming together in an unseen void, while the Big Bounce hinges on quantum gravity's ability to rewind collapse into expansion. One is a cosmic collision, the other, a quantum resurrection. Critics highlight a key hurdle, entropy. Each bounce should, in theory, amplify disorder, leaving subsequent universes more chaotic than the last. So why does our cosmos appear so finely tuned? Some theorists propose that quantum effects during the bounce could reset entropy, like shaking a snow globe to redistribute the flakes. Others speculate that information might be preserved across cycles, with the laws of physics subtly evolving with each rebirth. The Big Bounce isn't just a theory about the universe's past, it redefines its future. If true, our cosmos isn't racing toward an inevitable end but preparing for a metamorphosis. Stars will die, black holes will evaporate, but existence itself would continue, eternally reinventing itself in a rhythm older than time. It's a vision where endings are gateways and the universe is not a one-act play, but an encore without end. What if every action you take, every step, every word spoken, is mirrored perfectly in a parallel universe, but in reverse? This is the mind-bending premise of the mirror universe theory, where time itself could flow backward compared to our own. At first glance, it sounds like pure science fiction, but the roots of this idea dig deep into one of physics' most robust principles, CPT symmetry. This fundamental law states that if you flip a particle's charge, mirror its position in space, and reverse the flow of time, the laws of physics should remain unchanged. In other words, the universe doesn't care if you're watching it play forward or rewind, it operates the same way either direction. So how could this symmetry spawn an entire backward universe? The clues lie in antimatter, the enigmatic counterpart to ordinary matter. Every particle we know, electrons, quarks, neutrinos, has an antimatter twin with opposite charge. When matter and antimatter meet, they annihilate in a flash of energy. But here's the puzzle: if the Big Bang created equal amounts of both, why is our universe dominated by matter? One provocative answer suggests the missing antimatter didn't vanish, it formed a mirror universe where time runs in reverse. Picture two cosmic DVDs playing simultaneously. One spins forward, showing stars forming and civilizations rising. The other spins backward, with galaxies unraveling into primordial gas. The implications of this are staggering. In a mirror universe, cause and effect would flip. A cup shattering on the floor here might reassemble itself there. People wouldn't age, they'd grow younger, their memories unfolding in reverse. Even the arrow of entropy, which dictates disorder increases over time in our world, would point the opposite way, making broken things mend themselves spontaneously. Some theorists speculate these universes could be forever out of sync, separated by the Big Bang itself, like two sides of a coin that can never meet. Yet the theory faces fierce skepticism. If a mirror universe exists, why haven't we detected its influence? Shouldn't there be subtle gravitational tugs or quantum ripples bleeding through? Others argue CPT symmetry doesn't require an actual backward universe, just that the math allows for one. But supporters counter that certain anomalies in cosmic ray data and particle physics experiments could hint at hidden interactions with this inverted realm. Whether real or not, the mirror universe forces us to confront the strangeness of time itself. Is our perception of its flow just an accident of our matter-dominated perspective? If we could step outside our cosmic bubble, would we see time branching in both directions, like a river forking endlessly into the past and future? It's a reminder that even the most familiar aspects of reality might be shadows of something far more bizarre, a universe where every ending is someone else's beginning. What if our universe isn't expanding into some vast, empty void, but is instead trapped inside the belly of a cosmic beast? This is the startling premise of the black hole cosmology theory, where everything we see, stars, galaxies, even time itself, could be the interior of a higher dimensional black hole. Think of it like a Russian nesting doll. where our entire reality is just one layer hidden inside something far grander and more terrifying. At first glance, the math almost makes sense. Black holes warp spacetime so severely that their interiors become disconnected from the outside universe. To an observer inside the event horizon, the point of no return would appear not as a wall, but as an infinite expanse of space rushing outward. Sound familiar? That's eerily similar to our universe's expansion, where galaxies seem to flee from us as if space itself is stretching. Some theorists, like physicist Nikodem Poplawski, suggest this isn't a coincidence. The Big Bang singularity might have been the birth of a black hole in a parent universe, with our cosmos unfolding inside it like a flower blooming in reverse. But how could a universe fit inside a black hole? The key lies in extra dimensions. In our familiar three-dimensional world, black holes are spherical traps. But in higher dimensional space, they could form complex structures like four-dimensional hyperballs, whose 3D shadows appear as spheres. If our universe is the interior of such an object, its event horizon wouldn't be a surface we could reach, it would be the limit of our observable cosmos, forever receding as space expands. Every galaxy racing away from us would unknowingly be floating toward this unseen boundary, like leaves caught in a river flowing toward a waterfall we can never see. The theory makes bold predictions. If true, the cosmic microwave background, the afterglow of the Big Bang, might carry imprints of the parent universe's structure, like faint fingerprints left on a window. Some researchers even speculate that dark matter could be gravitational, leakage from higher dimensions, remnants of the black hole's formation. Others suggest looking for unusual patterns in the distribution of galaxies, anomalies that might reveal the hidden geometry of our cosmic prison. Yet skeptics raise sharp objections. If we're inside a black hole, why isn't everything collapsing toward a central singularity? Proponents argue that the outward rush of expansion inherited from the black hole's birth counters the inward pull of gravity, creating a precarious balance. It's like being in an elevator that's both falling and accelerating upward at the same time, a paradox that somehow holds the universe together. Whether cosmic coincidence or profound truth, the black hole universe theory forces us to rethink the nature of reality. Are we the product of a singular creation, or just the aftermath of another cosmos's collapse? If the answer lies in the depths of a black hole, it means the universe isn't just mysterious, it might be nested inside a mystery wrapped in an enigma, waiting for us to decode its darkest secrets. What if the fate of our universe isn't a slow fade into darkness but a violent cosmic shredding? This is the nightmare scenario of the phantom universe theory, where dark energy doesn't just accelerate the expansion of space, but grows stronger over time, eventually tearing apart the very fabric of reality. Picture an invisible force so relentless that first it rips galaxies from each other, then stars from their galaxies, then planets from their orbits until finally, even atoms are torn asunder in a catastrophic finale known as the Big Rip. Dark energy, the mysterious force pushing the universe apart, currently makes up about 68% of the cosmos's energy budget. For decades, scientists assumed its strength was constant, a steady pressure encoded in Einstein's cosmological constant. But what if it's not? Phantom energy is a hypothetical form of dark energy that doesn't just persist, it intensifies. Like a car's accelerator stuck in the floorboard, it would cause the universe's expansion to speed up exponentially, growing more ferocious as space stretches. The consequences are apocalyptic. Within a finite time, perhaps 100 billion years, this phantom force would overcome gravity, electromagnetism, even the nuclear forces binding atoms together. The timeline of the Big Rip reads like a horror story written by physics itself. First, galactic clusters would vanish beyond each other's cosmic horizons, their light stretched into oblivion. Next, individual galaxies would disintegrate as phantom energy overpowers their gravitational glue. Then, stars would detach from their planetary systems, drifting into an ever-expanding void. In the final hours, planets and stars themselves would rupture, their matter unable to resist the swelling tide of space, and in the last microseconds, atomic nuclei would explode as the strong nuclear force fails, leaving behind a cold, empty universe where not even particles can exist. This theory hinges on a single parameter, the equation of state of dark energy, represented by the value W. For the Big Rip to occur, W must be less than -1, a realm where dark energy's density increases as space grows. Current observations hover near this threshold, but uncertainties leave the door open. Some models even suggest phantom energy could warp spacetime so severely that it spawns wormholes or baby universes before the final rip, cosmic paradoxes where destruction births new realities. Yet skeptics argue nature abhors such extremes. A universe that tears itself apart seems too chaotic to align with the elegant symmetries we observe. Others counter that phantom energy might be a transient phase, a cosmic glitch that eventually stabilizes, but if the phantom universe is real, it paints a chilling portrait of our fate, not with a whimper, but with a scream that echoes across the void. What if the universe isn't built from matter or energy, but from something far more fundamental, pure information? This radical idea, known as the information universe theory, suggests that reality itself might be nothing more than a vast, interconnected web of data. Think of it like a cosmic computer where every particle, every force, even the fabric of spacetime, is just a collection of ones and zeros, flickering in and out of existence like pixels on a screen. It's a concept that blurs the line between physics and philosophy, challenging us to reconsider the very nature of existence. The roots of this idea trace back to quantum mechanics, where particles behave less like solid objects and more like probabilities, mathematical waves that collapse into definite states only when observed. Pioneers like John Wheeler, the physicist who popularized the term black hole, took this further with his famous phrase, "it from bit." In Wheeler's vision, every particle, every event in the universe is ultimately grounded in binary choices, answers to yes or no questions written into the fabric of reality. At its core, the universe isn't a collection of stuff, it's a network of information exchanges, a cosmic conversation where the act of observation creates what we perceive as real. This isn't just abstract theorizing. Quantum experiments like the double-slit test, where particles seem to know whether they're being watched, suggest that information plays a role deeper than we ever imagined. Even black holes, those cosmic data shredders, obey the laws of information conservation, hinting that nothing truly disappears, it just gets scrambled beyond recognition. Some physicists, like digital physics proponents, argue that the universe might literally run on computational rules, with Planck-scale pixels acting like the smallest possible units of reality, processing information in a cosmic algorithm we're only beginning to decode. But how could something as intangible as information give rise to stars, planets, and conscious beings? Imagine building a video game so detailed that its characters begin questioning their own reality. To them, the game's world feels solid, but at the code level, it's all data. Similarly, our three-dimensional experience might just be the user interface for a deeper informational layer. Even time could be emergent, a side effect of how information updates and rearranges itself like frames in a movie, creating the illusion of motion. The implications are staggering. If information is primary, then black holes aren't just gravitational monsters, they're the universe's hard drives, storing data in ways we don't yet understand. Dark matter and dark energy might be informational artifacts, glitches in the cosmic code, and consciousness. Some theorists suggest it could be a feedback loop, the universe's way of observing itself into existence. Critics argue that calling reality, information, just relabels the mystery without explaining it. What processes the information? What writes the rules? Others counter that we're glimpsing a deeper truth, one where math isn't just a tool to describe reality, but its very foundation. Whether cosmic code or metaphysical metaphor, the information universe theory forces us to confront a humbling possibility. Everything we see, touch, and are might just be the tip of a data iceberg, with most of reality's workings hidden beneath the surface. Imagine inflation, the furious expansion of space in the first moments after the Big Bang, never actually stopped. What if instead of slowing down, it's still happening right now in pockets of the cosmos, endlessly birthing new universes like bubbles in a boiling pot? This is the mind-bending heart of eternal inflation, a theory that reshapes our cosmic origin story from a singular event into an infinite, self-replicating process. The idea traces back to physicist Alan Guth, who first proposed cosmic inflation in the 1980s to explain why the universe appears so uniform on large scales. But the implications went far deeper than anyone expected. Inflation isn't just a one-time stretch, it's a runaway effect, a quantum domino that never truly stops. Picture a balloon inflating so rapidly that tiny regions of its surface bud off into their own separate balloons, each expanding at the same explosive rate. Now replace the balloon with space-time itself, and you've got eternal inflation, an ever-growing fractal of universes, each sealed off from the others, each with its own laws of physics. Here's how it works. Quantum fluctuations in the early universe could create tiny pockets where inflation's energy doesn't dissipate. These regions continue expanding exponentially, faster than light, while the space around them stabilizes into the calm cosmos we know. Inside these runaway zones, new quantum fluctuations trigger more inflationary bubbles, universes within universes, endlessly sprouting like branches on an infinite tree. Some bubbles might collapse instantly, others could harbor entirely alien physics, with extra dimensions or altered constants. Our universe, just one lucky bubble where inflation slowed enough for stars and galaxies to form. The math behind this is startlingly elegant. Inflation's energy field, called the inflaton, behaves like a ball rolling down a hill. Most of the time it settles at the bottom, ending inflation. That's what happened here. But in some regions, quantum jitters keep kicking the ball back uphill, perpetuating the expansion. The result is a fractal multiverse, where the number of bubble universes grows exponentially with time. There's no outside, no edge, just an eternally inflating sea spawning islands of reality. Critics argue eternal inflation is untestable, since these bubbles are forever beyond our cosmic horizon. Yet some scientists hunt for subtle clues. If our bubble universe collided with another in the distant past, the crash might have left scars in the cosmic microwave background, anomalous cold spots, or strange ripples in the afterglow of creation. Others suggest that the distribution of galaxies across the sky could betray our bubble's shape, like wrinkles in a soap film. What makes eternal inflation so compelling isn't just its audacity, but its inevitability. If inflation is quantum in nature, then statistically, it must happen forever somewhere. The multiverse isn't a fringe idea, it's the natural consequence of gravity and quantum mechanics playing out on cosmic scales. And if true, it means the Big Bang wasn't a beginning at all, but a local event in an infinite, self-renewing cosmos. Our universe isn't special, it's just one note in an endless symphony, playing variations on the laws of physics across an infinite canvas of space-time. What if every choice you make, every life you live has already happened, and will happen again endlessly, in an unbreakable loop? This is the haunting premise of the time loop universe theory, where time isn't a straight line but a closed circle, repeating itself like a cosmic record stuck on the same groove. In this model, the Big Bang isn't just the beginning, it's the end point of a previous cycle, the moment the universe folds back on itself to start anew. Stars aren't born, they're reborn. Civilizations don't rise and fall, they rise and fall in precisely the same way, over and over, trapped in an infinite replay of history. The idea of cyclical time isn't new. Ancient Hindu and Greek philosophers envisioned cosmic cycles spanning eons, but modern physics gives the concept startling credibility. Einstein's theory of relativity allows for solutions where spacetime curves back on itself, creating closed time-like curves, paths that loop into the past. If the universe's geometry is shaped just right, these curves could stretch across the entire cosmos, stitching the end of time back to its beginning. Picture a globe where traveling far enough east eventually brings you back west, except instead of space, it's time itself bending into a circle, but there's a glaring problem: entropy. The second law of thermodynamics insists disorder always increases, making each cycle slightly more chaotic than the last, so how could history repeat perfectly? Some theorists propose that at the endpoint of each cycle, quantum fluctuations reset entropy to its initial low state, like shaking a snow globe to redistribute the flakes. Others suggest that the universe doesn't repeat exactly, but evolves through variations, like a song played differently each time. String theory even offers a potential mechanism: colliding branes in higher dimensions could violently recycle the cosmos, wiping the slate clean with each collision. The philosophical implications are dizzying. If time loops eternally, free will becomes an illusion. Every decision you agonize over was predetermined in the last cycle, and will unfold identically in the next. Your triumphs, your regrets, even this moment of reading these words would be an echo of countless past iterations. The universe wouldn't be a story with a beginning, middle, and end. It would be a single sentence written in a circle, readable no matter where you start. Could we ever prove such a loop? Some physicists hunt for anomalies in the cosmic microwave background, subtle patterns that might betray a previous cycle's final moments. Others suggest that gravitational waves from colliding black holes could carry echoes of prior universes, like ripples crossing a pond in reverse, but the most chilling evidence might be déjà vu itself, those uncanny moments of recognition that feel like memories of a life already lived. Are they glitches in the mind, or faint recollections of a time we've looped through before? Whether cosmic truth or poetic speculation, the time loop universe forces us to confront the nature of existence itself. Are we writing our own story, or just reading the same page over and over, unaware the book's spine is a circle? In a universe without true beginnings or endings, even the act of questioning our fate might be part of the script, a line spoken infinite times before, and infinite times yet to come. At the smallest scales imaginable, far smaller than an atom, spacetime might not be the smooth, unbroken fabric we perceive, but a chaotic, frothing sea of virtual particles popping in and out of existence like bubbles in a boiling pot. This is the bizarre world of quantum foam, a theory suggesting that the very foundation of reality is anything but stable. Imagine zooming in on the surface of a calm pond until you see it's actually a storm of microscopic ripples, constantly churning. That's what the universe might look like at the Planck scale, where space and time lose their certainty and become a turbulent foam of fleeting energy. This idea emerges from the clash between Einstein's general relativity, which paints spacetime as a smooth, continuous stage, and quantum mechanics, where everything is granular, probabilistic, and uncertain. At the quantum level, empty space isn't empty at all. It crackles with pairs of particles and antiparticles flickering into existence for fleeting moments before annihilating each other, borrowing energy from the vacuum in a cosmic balancing act. This quantum jitter warps spacetime itself, turning what appears solid into something more like a froth of microscopic black holes and wormholes, constantly forming and dissolving in unimaginably short bursts. One of the most radical implications: if spacetime is foamy, it might be threaded with temporary wormholes and tiny bridges linking distant points in space, or even different moments in time. These wouldn't be the stable, traversable tunnels of science fiction. They'd be vanishingly small, lasting only fractions of a second before collapsing. But some theorists suggest that under extreme conditions, like near the singularity of a black hole or in the earliest moments of the Big Bang, these wormholes might stretch and stabilize, becoming cosmic shortcuts or even gateways to other universes. The quantum foam also offers clues to one of physics' greatest challenges, unifying gravity with quantum mechanics. While the other fundamental forces, electromagnetism, the strong and weak nuclear forces play by quantum rules, gravity stubbornly resists. But if spacetime itself is a seething quantum foam at its core, then gravity might emerge from this chaotic dance, like waves rising from the ocean's choppy surface. Some models even suggest that the foam structure could explain dark energy, its fluctuations driving the accelerating expansion of the universe, proving the existence of quantum foam isn't easy. Its effects would be vanishingly small, detectable only at energies far beyond our current technology, but scientists have proposed ingenious experiments, like studying high-energy gamma rays from distant quasars. As these photons travel billions of light-years, tiny fluctuations in spacetime's foam might subtly alter their paths or energies, like light shimmering through a heat haze. So far, results are inconclusive, but the hunt continues. If true, the quantum foam theory rewrites our understanding of reality at the deepest level. The universe isn't just a stage where particles move, it's a dynamic, seething entity, alive with energy and possibility, and somewhere in that foam, hidden beneath the surface of our perceptions, might lie the keys to wormholes, time travel, and the ultimate unification of physics itself, if only we could peer closely enough. What if the entire universe is thinking, not metaphorically but literally, with galaxies acting like neurons in a cosmic brain, and the laws of physics functioning as its learning algorithm? This is the spine of the neural network universe theory, where reality itself might be a vast, self-organizing system eerily similar to the artificial intelligence we're building here on Earth. At first glance, it sounds like science fiction, but recent breakthroughs in physics and machine learning reveal uncanny parallels between how the cosmos evolves and how neural networks process information. The idea hinges on a startling observation: the structure of the universe's large-scale web filaments of galaxies, stretching across billions of light-years, bears a striking resemblance to the interconnected neurons of a biological brain or the layers of a deep learning AI. Both systems rely on networks where nodes, whether neurons or galaxies, communicate, adjust connections, and transmit signals that shape the whole. In a neural network, weights between neurons determine how information flows. In the cosmos, gravity and dark matter dictate how galaxies cluster and interact. Both systems exhibit emergent complexity, simple rules giving rise to intricate, unpredictable behavior. This isn't just a visual metaphor. In 2018, physicist Vitaly Vanchurin proposed that the universe might literally be a neural network at its most fundamental level. His equations suggest that quantum mechanics and general relativity, the two pillars of modern physics, could emerge naturally from a system operating like a machine learning model. Imagine training an AI to recognize patterns in data, and instead of spotting cats in photos, it inadvertently learns the laws of physics as its optimization strategy. In this view, particles aren't tiny billiard balls but nodes in a computational graph, and spacetime itself could be an emergent property of information processing. The implications ripple outward. If the universe learns and adapts like an AI, it might explain why physical constants appear fine-tuned for complexity. Just as a neural network adjusts its parameters to minimize error, the cosmos could have self-organized into its current state through a kind of cosmic trial and error. Even the arrow of time might reflect this learning process, a forward direction, because the universe remembers more as it evolves. Supporters point to entropy's resemblance to loss functions in machine learning, where systems naturally trend toward states of equilibrium unless driven by external, or in this case, intrinsic optimization. Critics argue this is just an analogy stretched too far, that similarity in structure doesn't imply identical function, yet experiments hint at deeper connections. Quantum entanglement, where particles instantly influence each other across vast distances, mirrors how weights in a neural network adjust globally when trained. Some researchers even simulate universes using neural nets to study cosmic inflation, finding that AI-generated structures can mimic real galaxy distributions. If the math holds, we might be living inside a learning system so vast, its thoughts are galaxies and its memories are written in the stars. Whether profound truth or provocative metaphor, the neural network universe challenges us to rethink reality's nature. Are the laws of physics just the training rules of some unfathomable intelligence? Is consciousness not a product of the universe, but the universe itself awakening? The theory doesn't just ask what lies beyond space, it asks whether space is a mind, and if so, what it's thinking about next. What if everything we think we know about the universe, its origins, its structure, even the forces that shape it, is built on a fundamental misunderstanding? The plasma universe theory dares to ask this radical question, flipping conventional cosmology on its head by proposing that electricity, not gravity, is the dominant force weaving the cosmic web. Forget dark matter, black holes, and even the Big Bang. This controversial model paints a universe alive with electric currents, where galaxies are strung along vast, glowing filaments like beads on a wire, and laboratory experiments on Earth hold the key to understanding the cosmos itself. The roots of this idea stretch back to the early 20th century, when Norwegian physicist Christian Birkeland first proposed that the northern lights were powered not by atmospheric gases alone, but by electric currents flowing from the sun. His experiments with charged particles in vacuum chambers, dubbed terrella, mimicked the behavior of cosmic plasma so accurately that mainstream science initially dismissed it as too simplistic. Yet today, plasma physicists point to those very experiments as a Rosetta Stone for interpreting the universe. Plasma, often called the fourth state of matter, isn't just the stuff of stars. It makes up over 99% of the visible universe, from the ionized gas between galaxies to the swirling arms of nebulae. In the plasma universe model, these ionized clouds aren't passive bystanders but active players, shaped by electromagnetic forces far stronger than gravity across cosmic distances. Take the vast filaments connecting galaxy clusters, structures spanning hundreds of millions of light years that conventional theories struggle to explain. Plasma cosmology suggests these are colossal Birkeland currents, cosmic scale versions of the currents that power neon signs, carrying electricity across the void. Just as electric discharges in a lab form twisting, filamentary patterns, so too might the universe organize itself along invisible lines of magnetic force, with galaxies forming at the intersection points like knots in a net. This perspective turns many astrophysical puzzles on their heads. Quasars, often explained as supermassive black holes feeding on gas, might instead be electrified plasma beams, natural particle accelerators operating on scales we can barely comprehend. The rotation curves of galaxies, which famously require dark matter to explain under gravity-based models, could arise from the magnetic fields generated by intergalactic currents. Even the cosmic microwave background, hailed as evidence for the Big Bang, might be reinterpreted as the glow of a universe forever renewing itself through electrical interactions. But why hasn't this theory gained wider acceptance? Detractors argue that while plasma physics explains local phenomena like solar flares, scaling it up to galactic proportions requires assumptions about conductivity and charge separation that defy observational evidence. Others point out that gravity's dominance on large scales is backed by overwhelming data, from planetary orbits to gravitational lensing, yet plasma cosmologists counter that space isn't the perfect vacuum we once thought. Even the sparse plasma between stars can conduct currents over cosmic timescales, subtly shaping the universe in ways gravity alone cannot. Perhaps the most compelling aspect of the plasma universe isn't its rejection of mainstream ideas, but its testability. Unlike dark matter or string theory, plasma effects can be recreated in laboratories today. When researchers zap a plasma-filled chamber with high voltage, the resulting filaments, plasmoids, and helical structures bear an uncanny resemblance to the structures we see in deep space. It's a rare cosmological model where the evidence isn't locked away in telescopes or supercomputers, but sparking right in front of us if we're willing to look. Whether the plasma universe ultimately rewrites our cosmic story or remains a provocative alternative, it serves as a vital reminder: sometimes the universe's greatest mysteries aren't hidden in the distant unknown, but embedded in the flicker of a lab plasma, waiting to be read. What if the holographic principle doesn't describe just our universe, but an infinite stack of them, each a lower dimensional shadow cast by realities we can't see? This is the mind-melting fusion of the holographic multiverse theory, where the fabric of existence isn't just a projection, but a kaleidoscope of reflections, each universe a distorted echo of something grander unfolding in dimensions beyond our grasp. Imagine standing between two mirrors, watching your image repeat into infinity except instead of reflections, each layer is a self-contained cosmos, its laws of physics warped like light passing through fractured glass. At the intersection of string theory and quantum gravity, this idea takes the holographic principle where our 3D universe could be encoded on a 2D boundary and scales it to multiversal proportions. Picture a towering skyscraper where each floor represents a universe, but the higher you go, the more dimensions unfold. Our reality might be a 3-dimensional shadow cast by a 4 or 5-dimensional structure above, which in turn could be a shadow of something even higher, ad infinitum. In this fractal hierarchy, every universe is both real and an illusion, its substance dependent on the vantage point of the observer. The math behind this is as elegant as it is strange. Juan Maldacna's ADS/CFT correspondence, a landmark discovery in string theory, showed that a higher dimensional space with gravity, like our universe, could be perfectly described by a lower dimensional system without gravity, operating purely through quantum fields. Now extend that idea across infinite layers: a 4D universe projecting our 3D reality, a 5D world projecting that 4D one, and so on. Each layer isn't just a copy, it's a coarse-grained approximation, like a pixelated image of a higher resolution original. The pixels of our reality, Planck-scale units of spacetime, might be artifacts of this cosmic compression, blurring the finer details of the dimensions above. But here's where it gets wild. If higher dimensions exist, their physics could bleed into ours as anomalies, subtle deviations in gravity, unexpected particle behaviors, or even dark matter itself. Some theorists propose that quantum entanglement, where particles instantly influence each other across vast distances, might actually be a shadow effect. The particles aren't communicating faster than light, they're tethered by unseen connections in a higher D-reality. Similarly, the inexplicable fine-tuning of our universe's constants, the precise balance allowing stars and life to exist, could reflect the stable geometry of a parent universe we'll never see. Critics argue this is metaphysics disguised as physics, a tower of abstractions with no experimental hook, yet supporters point to glimmers of evidence. If our universe is a hologram, its data limit should imprint on high-energy phenomena, like gamma rays scattering at ultra-fine scales. Others hunt for anomalous, cosmic structures, galactic alignments, or voids that defy statistical likelihood, which might be fingerprints of higher dimensional topology pressing through. Even the controversial cold spot in the cosmic microwave background has been theorized as a bruise from a collision with another universe's brane in the holographic stack. The holographic multiverse doesn't just expand our cosmic address, it shatters the illusion of separateness. Every choice, every event in our world might ripple upward, influencing realities we'd consider myth, while their unseen dimensions sculpt ours from the shadows. It's a vision where the multiverse isn't just parallel, it's hierarchical. a hall of mirrors where every reflection holds a universe, and every universe is someone else's reflection. What if our entire universe is just a statistical blip, a fleeting bubble of order in an infinite, lifeless void? The quantum fluctuation theory dares to suggest exactly that. Everything we see, from the farthest galaxies to the beating of our own hearts, might owe its existence to nothing more than a random tremor in the fabric of nothingness. Picture a vast featureless ocean where every so often, a single wave surges for no reason at all, cresting briefly before dissolving back into the quiet. Now replace the ocean with an eternal void, and the wave with our cosmos, an accidental eddy in the emptiness, destined one day to fade without a trace. The roots of this idea dig deep into one of quantum mechanics' strangest quirks: virtual particles. Even in a perfect vacuum, space isn't truly empty. Particle-antiparticle pairs constantly blink into existence, borrowing energy from the void before annihilating each other, all within fractions of a second. These microscopic fluctuations are no mere theory. They've been measured in lab experiments like the Casimir effect, where two metal plates placed impossibly close together feel a subtle push from these ghostly particles. But if quantum mechanics allows such fleeting distortions, why couldn't a fluctuation on an unimaginably grander scale birth an entire universe? This possibility hinges on a startling property of our cosmos: its net energy might be zero. When you tally the positive energy of matter and motion against the negative energy of gravity, the sum cancels out. In essence, the universe could be the ultimate free lunch, a self-contained bubble where nothing was ever created in the classical sense, just temporarily rearranged from the void. Physicist Edward Tryon first proposed this in 1873, suggesting our universe is a rare but inevitable quantum event in an otherwise inert multiverse. No divine spark, no cosmic explosion from nothing, just the statistical inevitability that given infinite time, even the most improbable fluctuations must occasionally occur. The implications unravel like a cosmic hall of mirrors. If one quantum fluctuation spawned our universe, countless others might be perpetually bubbling up in the void, each with its own physics, its own timeline. Some would collapse instantly, snuffed out by their own instability. Others might expand just enough to form ephemeral pockets of structure before dissolving. A select few like ours could strike the delicate balance needed to persist for billions of years, fostering galaxies, stars, and minds capable of pondering their own accidental origins. Critics argue this pushes quantum mechanics beyond its known limits. Virtual particles borrow energy for nanoseconds, not eons, but proponents counter that in a true void, without time or observers, quantum events might operate differently. Inflation theory's rapid expansion could then lock in a fluctuation's energy, preserving it against immediate collapse. Others speculate that dark energy's mysterious push might be the remnant of this initial quantum kick, a faint echo of the universe's improbability. The theory's true power lies in its austerity. It needs no multiverse, no higher dimensions, no unseen creators, just the known laws of quantum physics stretched to their ultimate conclusions. Yet it leaves us with a paradox. If we're the product of pure chance, why does the universe feel so finely tuned for complexity? The answer might be bleakly beautiful: we're not. We're just the rare fluctuation where conditions align to ask the question. The stars, the planets, the very atoms in your hands, they're not meant to be. They simply are for now, in this fleeting eddy of order before the void reclaims it all. What if consciousness isn't something the universe produces, but something it is? This is the radical proposition of panpsychism, the theory that consciousness isn't an emergent property of complex brains, but a fundamental feature of reality itself, as intrinsic to existence as space, time, or gravity. Imagine a cosmos where every atom, every star, every ripple of light hums with the faintest glimmer of subjective experience, not thinking, not self-awareness as we know it, but a raw, primal form of inwardness woven into the fabric of space-time. It's a concept that blurs the line between physics and philosophy, challenging our deepest assumptions about what it means to be alive. The roots of panpsychism stretch back millennia, from ancient Eastern philosophies to Renaissance thinkers like Giordano Bruno. But modern science lends it startling plausibility. Take the infamous double-slit experiment, where particles behave like waves when unobserved, spreading out in probability clouds, but snap into definite states the moment they're measured. This observer effect suggests that consciousness might play an active role in shaping reality, collapsing quantum possibilities into concrete events. Nobel laureate Eugene Wigner even speculated that consciousness causes the collapse, implying the universe requires observation to manifest itself fully. Critics dismiss this as misinterpretation. Quantum effects don't need human minds, just interaction with any macroscopic system. Yet panpsychists argue the underlying mystery remains: why does observation do anything at all? If consciousness is truly emergent from non-conscious matter, how does inert stuff like atoms suddenly spark subjective experience? This hard problem, coined by philosopher David Chalmers, exposes a gap in materialist explanations. Panpsychism offers an elegant, if unsettling, solution. Subjectivity was never absent to begin with. The implications cascade like dominoes. If consciousness is fundamental, then the universe might possess a form of proto-mind, a vast, diffuse network of experience where complexity amplifies awareness. A human brain wouldn't generate consciousness, it would channel it, like a whirlpool concentrating the flow of water. Even stars and galaxies could participate in this cosmic sentience, their gargantuan processes humming with a slow, unfathomable inner life. Neuroscientist Giulio Tononi's integrated information theory offers a math-backed angle. Consciousness arises wherever information is integrated in specific ways, meaning even simple systems, from thermostats to trees, might harbor trace amounts. Philosopher Philip Goff suggests we imagine consciousness as spacetime's dark matter, invisible to instruments yet omnipresent, detectable only through its effects. Skeptics counter that panpsychism explains nothing, it just relabels the mystery. How do tiny mind bits combine into rich experiences like love or déjà vu? And why haven't we detected this universal consciousness? Supporters reply that we're like fish searching for water. You can't find what you're made of with tools made from it. Whether cosmic truth or poetic metaphor, panpsychism forces a reckoning. The universe might not just contain minds, it might be one, dreaming itself into existence, one observation at a time. What if the universe isn't just described by math? What if it is math? Not just a language we use to decode reality, but reality itself, an intricate web of pure mathematical structure where everything from electrons to galaxies are simply equations playing out in an abstract space. This is the mind-bending core of the mathematical universe hypothesis, championed by physicist Max Tegmark, who argues that existence isn't governed by numbers, it's made of them. Imagine a cosmic Sudoku grid where the numbers aren't written in cells, they are the cells, and the grid stretches infinitely in dimensions we can't perceive. Tegmark breaks this idea into 4 escalating levels, each more radical than the last. Level 1 is familiar: the universe operates by mathematical laws, like Newton's equations for gravity or Schrödinger's wave function. This is uncontroversial. Science already treats math as the universe's operating system, but level 2 pushes further. Not only does math describe reality, but all possible mathematical structures exist physically. Our cosmos is just one specific solution to a grand equation, while others might harbor alien physics universes where time has 2 arrows or gravity repels. It's the multiverse idea on steroids, with every consistent math construct spawning a real, tangible world. Level 3 is where things get truly wild. Here, Tegmark invokes the quantum many-worlds interpretation, where every quantum decision branches reality into parallel timelines, but in his framework, these branches aren't just possibilities, they're mathematical inevitabilities, as real as the digits of pi unfolding in an infinite sequence. Your life isn't a single path, it's a fractal of every conceivable variation, each encoded in the equations, and then there's level 4, the ultimate abstraction. All mathematical structures exist, full stop. Not just the ones that fit our physics, but every conceivable configuration, from hypercubes in 11 dimensions to logic systems where 2 plus 2 equals blue. In this view, our universe is no more special than a single term in an infinite polynomial. The implications are dizzying. If reality is purely mathematical, then consciousness itself might be an algorithm, a self-referential loop in the computation. Even the sensation of free will could be an emergent property of deterministic equations, like a character in a video game believing they're making choices when their actions are preset by code. Tegmark suggests we're self-aware substructures in the math, patterns that perceive themselves as real. This echoes Pythagorean mysticism, an ancient belief that numbers are the essence of existence, but with the rigor of quantum field theory and topology. Critics, however, sharpen their pencils. Philosopher Nick Bostrom questions whether abstract math can cause anything without a physical substrate. Can an equation truly be a star? Others argue the hypothesis is untestable, reducing to the tautology that the universe is what it is. And then there's the wrong math problem. If every possible structure exists, why do we perceive this specific, seemingly arbitrary set of rules? Tegmark counters that observers can only arise in structures complex enough to support them, a cosmic anthropic principle where the math selects for its own witnesses. Yet the theory's brilliance lies in its austerity. It needs no mystical substances or hidden dimensions, just the cold, beautiful logic of mathematics. Whether ultimate truth or elegant oversimplification, it forces us to confront a haunting possibility. We might not live in a universe of things, but in a universe of thoughts, where the only real substance is the eternal dance of numbers in the void. If every possible universe that math can describe actually exists, then reality isn't just vast, it's everything. This is the dizzying conclusion of Max Tegmark's ultimate ensemble theory, where existence isn't a single cosmos with fixed rules, but an infinite library containing every conceivable variation of physics, dimensions, and logic. No equation is left unsolved, no structure unrealized. Universes where gravity pushes instead of pulls, they're out there. Realities where time loops like a Möbius strip or space has 12 dimensions. Already written into the cosmic ledger, even worlds made of pure sound, or where consciousness arises from fractal patterns in dust, must exist somewhere in the ultimate multiverse. At first glance, this seems like a philosopher's thought experiment gone rogue, but Tegmark grounds it in ruthless logic. If reality is purely mathematical, as his earlier levels suggest, then there's no reason to privilege our particular set of equations. Math doesn't have favorites, the same way every possible combination of a deck of cards must appear if you shuffle enough times. Every consistent mathematical structure must manifest as a physical universe given infinite possibility. The result is a cosmic kaleidoscope where every twist births entirely new laws of nature, unconstrained by human intuition. The implications spiral into existential vertigo. Consider the combinatorial madness of a reality where every parameter is dialed to every possible value. There are universes where the speed of light is a sluggish 10 miles per hour, turning interstellar travel into a weekend road trip, and others where light moves so fast that time barely flows. Some cosmic variants might be stillborn, collapsing instantly into quantum foam, while others could simmer for eternity as featureless soups of entropy. And lurking in the statistical noise, universes indistinguishable from ours, except your left sock is missing, or Napoleon won at Waterloo, or the very concept of left socks or Waterloo never existed at all. This is where the anthropic principle becomes our only lifeline. In an infinite ensemble of universes, most would be inhospitable to life, no stable atoms, no stars, just chaotic voids or frozen wastelands. We find ourselves in a universe that allows us to exist because, well, we couldn't ponder the question otherwise. It's not that our cosmos is special, we're just the lucky lottery winners who drew a ticket where the numbers added up to complexity. Tegmark's framework takes this further. Even the most bizarre universes might harbor forms of life. We can't recognize self-replicating patterns in plasma, or sentient quantum fields that perceive reality through equations rather than senses. Critics pounce on the theory's unfalsifiability. If every possible universe exists, how could we ever test it? And why does math, a human invention, hold such privileged sway over reality? Tegmark's rebuttal is sly. Math isn't invented, but discovered. The Mandelbrot set's infinite complexity existed before humans named it, just as prime numbers underpin the cosmos long before Pythagoras. The ultimate ensemble doesn't rely on our scribblings. It's the other way around. Our math is a dim reflection of the structures that must be, yet the theory's grandeur is also its strangeness. It suggests that every nightmare, every daydream, every fictional world you've ever imagined exists somewhere in the multiverse's inventory. The borders between real and possible dissolve. And if that's true, then the ultimate mystery isn't why our universe exists, it's why we perceive this one slice of the infinite instead of all the others. The answer might be as simple as this: we're not the universe's main character, we're just one footnote in an encyclopedia too vast to read. From parallel worlds where time runs backward to cosmic holograms projecting our reality from a two-dimensional edge, we've ventured through some of the most daring ideas about what lies beyond our universe. Each theory, whether the brain-bending holographic principle or the haunting Boltzmann brain paradox, challenges not just our understanding of space and time, but the very nature of existence itself. Some, like the multiverse, find roots in cutting-edge physics, while others, like the simulation hypothesis, blur the line between science and philosophy. Yet they all share one thing: the audacity to question whether our universe is all there is or just a speck in an unfathomable expanse of possibilities. Think about the sheer scale of these ideas. One moment we're floating inside a higher dimensional black hole, the next we're pondering if our lives are loops in an endless cosmic replay. The wildest part: none of these theories can be dismissed outright. They emerge from equations scribbled by Nobel laureates, from anomalies in the cosmic microwave background, from the eerie behavior of particles in quantum labs. Reality, it seems, is far stranger than fiction, and the more we learn, the more the boundaries of the possible expand. So which theory captivates you? Do you find elegance in the hologram's cosmic code? Or does the drama of a big rip speak to your inner apocalyptic visionary? Maybe you're drawn to the quiet terror of the false vacuum, the idea that everything we know could vanish in an instant, rewritten by a quantum hiccup. Drop your favorite in the comments below. We're endlessly curious about which cosmic rabbit holes you dive into next, and if these mysteries left you hungry for more, don't forget to subscribe. The universe is vast, and we've barely scratched the surface of its secrets. From hidden dimensions to time-bending anomalies, there's always another enigma waiting just beyond the edge of understanding. Thanks for joining us on this journey to the far reaches of reality, where every answer only leads to deeper, darker, and more dazzling